This is the second half of my talk on stable complete length in graphs of groups. At the end of the first part, we mentioned that there are two steps going into the proof of the main theorem. First, we simplify admissible surfaces into simple normal form. This makes admissible surfaces more structured. Using this structure, we can turn the problem of computing stable complete length into a linear programming problem. In order to introduce the simple normal form, we first need to extend the class of admissible surfaces to the class of relative admissible surfaces. And the reason is that there are natural operations that simplifies admissible surfaces. However, after simplification, the surface we get, they are only admissible in the relative sense. Recall that in the definition of an admissible surface for a given loop gamma, we require all the boundary components to wrap around gamma, possibly several times. In a relative admissible surface, we allow certain boundary components to wrap around curves that are supported in vertex spaces. And here's an example. We take a wedge of two spaces. So the space here corresponds to a free product of two groups. And let's take the target curve to be the commutator of two elements, A and B, in the two factor groups. Now we can build a relative admissible surface as follows. Here we map the two blue parts to the wedge points. Then on the boundary of the middle rectangle, we get an element which is B times B inverse on the B side. So it bounds a disk on the B side. For the two remaining parts, we just bound them by an annulus. Then this introduces two new boundary curves, one representing A inverse, the other representing A. So this gives a relative admissible surface. It has one boundary component wrapping around the given loop gamma and two extra boundary components representing A and A inverse supported in the vertex groups. Note that in this case, we can actually add an annulus to close up the surface to make it into a genuine admissible surface. However, adding an annulus does not change the Euler characteristic. So the main point of introducing the relative admissible surface is that we can actually work with these simpler pictures, which doesn't really change the notion of complexity. And here's what's going on in general. In the definition of stable complete length, we can take the infimum of the same complexity but over relative admissible surfaces instead. Since relative admissible surfaces form a larger class, the number we get is a priori smaller. However, when the stable complete length of all the vertex groups is trivial, then this is actually an equality. And the reason is that having trivial stable complete length, that means whenever we have a collection of non-homologous groups supported in each vertex group, this infimum is 0. That means we can add some surface supported in the vertex space to close up these extra boundary components, but it increases the complexity by an actually small amount. So in the limit sense, we get an equality. Now we can introduce the simple normal form. And this example is one that's already in the simple normal form. It consists of these small parts. Each of them is either a disk on annulus, and each is supported in the vertex space. Here's what happens in general. Suppose we have a surface that is admissible or relatively admissible, like the one in the picture. Here, the boundary red curve represents those boundary components that wrap around the given loop gamma. The pink loop here represents some possible actual boundary components that are supported in vertex spaces. We can make the surface transfers to all edge spaces up to a homotopy. Then the preimage of the union of all edge spaces gives us a collection of proper arcs and embedded loops that are disjoint from each other. Cutting along these blue parts, namely the preimages, we can decompose the surface into small pieces, and each component is supported in a vertex space. There are essentially two types of boundary components for these small pieces. Either a loop boundary, like the one that wraps around some loop in some edge space, or a polygonal one, like the one over here. We can see such a component whenever we have a proper arc. This is because every proper arc connects to a red curve on the boundary. So on such a polygonal boundary, we necessarily have this alternating phenomenon between blue and red. Following every proper arc, there should be an arc that's supported on the given loop gamma. Then when the given loop gamma hits another edge space, we should the polygonal boundary must follow by another proper arc in blue, and then it alternates in this pattern. Now we can simplify each small piece into either a disk or an annulus, and here's how. Whenever we see a polygonal boundary, if it already bounds a disk like the one over here, then we do nothing. If it is contained in a more complicated component, like the one that we look at, for example, one in this component in the middle, this component has two polygonal boundary components, one on the left and one on, at the bottom, and also has an actual boundary, which is a loop boundary. In this case, what we do is we cut out a tubular neighborhood of each polygonal boundary. Then we'll have some subsurface that witnesses no polygonal boundary at all. And what we do is just throw such a component away. And similarly for this component, we'll cut out a tubular neighborhood of this polygonal boundary and throw away this annulus. After throwing away these components, we get a new surface that is also relatively admissible. And the components that we throw away necessarily has a non-positive order characteristic. So the new surface has smaller complexity. So it's simpler. So this operation tells us that whenever we start with a relative admissible surface, we can do this kind of cutting to reduce it to the so-called simple normal form. And the new surface has smaller complexity. So formally, we say such a surface is in simple normal form if each component or each small piece is either a disk or an annulus. And moreover, each piece exactly has one polygonal boundary. When it is an annulus, there is another boundary component, which is a loop supported in the corresponding vertex space. Now, to determine whether a piece should bound a disk or not, we can look at its polygonal boundary. reading off the boundary, we get an element in the vertex space, or rather the vertex group. If that group element is identity, then it bounds a disk. And this is if and only if. In the case of bomb select solitary group, the vertex group is just Z. So we are really dealing with numbers, and we can call the boundary element to be the winding number of the corresponding piece. And that winding number is 0 if and only if it bounds a disk. Remember that the goal is to minimize this normalized negative Euler characteristic. The Euler characteristic of the whole surface by Meyer-Vietoris, it is the sum of the Euler characteristic of these smaller disk or annulus pieces minus the number of these blue arcs. It's easy to show that the number of the blue arcs divided by n is proportional to the number of times that the given loop gamma hits the edge spaces. So it is a constant. Then to minimize the negative Euler characteristic is to maximize the number of disk pieces, because all the essential contribution to the Euler characteristic comes from these pieces, and each of them is either a disk or an annulus. Having as many disks as possible makes the surface as simple as possible. In this way, we can formulate the problem into a linear programming problem. So what we do is that for each possible type of the piece, we introduce a variable, corresponding variable. The variable tells us how many copies of this kind of piece appears in our surface, and we divide that number by the degree of the surface. Then the objective is to maximize the number of disk pieces. So that is to sum up all the variables corresponding to disk pieces. In particular, this is a linear function. There are also some linear constraints, making sure that, for example, these blue arcs pairs up perfectly so that we can glue things up without having any blue arcs that's left over. That's called the gluing condition. There's also a normalizing condition, making sure that in the normalized sense, on the boundary, we see exactly one copy of the given loop gamma. This looks good, except that possibly the linear programming is infinite dimensional, because possibly we have infinitely many possible types of these small pieces. In particular, this is infinite dimensional in an essential way when the edge group is infinite. Because even if we fix this combinatorial type of the piece, the red arcs has only finitely many choices because they all come from the given loop. The problem comes with these blue arcs, because each blue arc wraps around this edge space. So it represents some elements in the edge group. And when the group is infinite, each blue arc, its behavior has infinite many choices. That gives us infinite many pieces whenever we see such a blue arc. So the key is to reduce the linear programming to a finite dimensional one. And here's the trick. We fix a suitable positive integer d. Remember that a piece bounds a disk if and only if its winding number is 0. Now we relax this and considering all those with winding numbers divisible by this fixed number d as disks. So we call these disks, these pieces disk-like. Then we can define a new Euler characteristic where we count every disk-like as a disk. That is, each such a piece contributes 1 to the Euler characteristic. Then this gives us a new notion of complexity, which is no more than the original one. Then taking the infimum over all relative admissible surfaces, what we get is something no more than the stable commutator length. And the key lemma is that there's a suitable choice of this integer d depending on the loop and on the group, such that this inequality becomes equality. And this is done as follows. Start with an arbitrary relative admissible surface in normal form. We possibly has lots of disk-like pieces, but there's a way to find a suitable finite cover of the surface such that there's a way to adjust the winding numbers of these disk-like, the pre-images of these disk-like pieces in the cover, so that a large proportion of them can be realized as genuine disks. And this proportion can be taken to be as close to 1 as we want. This would prove the reverse inequality. Once we have established this key lemma, the advantage is that we can use this new Euler characteristic to do the linear programming. And the key is that we just need to know the winding number mod d to know whether a piece is disk-like or not. That allows us to just encode a finite amount of information from all those blue edges, which originally had infinitely many choices, but now if we take its winding number mod some finite number, it has only finite many choices. Now let me explain how to asymptotically promote a large proportion of disk-like pieces into disk pieces in the suitable large finite cover. The finite covers that we consider are of the following type. Starting from an arbitrary relative admissible surface in normal form. It's made of these small pieces, and there's a graph encoding how these pieces are glued together. We can take a finite cover of that graph. And then there's an induced finite cover for the surface. These are the surfaces that we consider. Now, what we are going to do is to adjust the winding numbers upstairs in the finite cover. But let's first look at how to adjust the winding numbers downstairs. Fix a co-orientation for the edge space. Then at every pre-image of the edge space, namely these blue arcs, there's an induced co-orientation. Now, for each blue arc, let's say, let's give it the orientation coming from the left-hand side piece. We can let this blue arc to wrap around the edge space k more times. This will change the winding number for this piece on the left by k times m. But it also changes the winding number for the piece on the opposite side. Since it has the opposite induced orientation, the winding number over there will be decreased by k times l. This is nice if the winding number that we start with is divisible by m. In that case, we can choose a suitable k and kill this winding number after the adjustment. And we can think of this as abstractly as pushing this winding number to the nearby piece. And the way the winding number changes is by the following rule. If we follow the opposite direction of the co-orientation, then the winding number, once we transfer to the next piece, becomes the original winding number times L divided by M. And if we go in the opposite direction, then it is divided by L and multiplied by M. And what is nice here is that we can do a sequence of this kind of adjustment assuming the winding number is always has enough copies of M and L as factors, what we can do is to do this kind of pushing following a boundary component. The boundary component wraps around the given loop gamma several times. And gamma, since it is now homologous, its intersection number with the edge space is 0. Here I mean the outbreak intersection number. So if we do this pushing along a full copy of gamma around some boundary component of the surface, half of the time we multiply the winding number by M and divide by L, and the other half of the time we do the opposite. So if we push the winding number along the boundary by a full copy of gamma, then the winding number possibly is pushed into a different piece, but the number doesn't change. So we can keep. So assuming we can, the winding number we start with has enough copies of M and L. Let's say it has enough copies of M and L as factors, where this number is greater than the geometric intersection number of the curve, the given loop gamma with the edge space. Then we are guaranteed to be able to push this along a full copy of gamma. Then we can keep doing this until we arrive at the piece that to start with by pushing a full round around a boundary curve. Downstairs, this does nothing because the winding number gets pushed all the way back, and we arrive at the same winding number. So this abstractly, this is described by the lower half of the picture. The pink dot represents the piece that we start with, which has a winding number that has large enough numbers of factors of M and L. And then we can push it along the some boundary component, and we can push the full round and come back with the same number. But now if we take a finite cover that's induced from taking the finite cover of the graph encoding the gluing, let's say there's a pre-image of this boundary curve that's a degree 6 cover. Then we will see 6 copies of this this piece in the finite cover along this boundary. Then we can do the same following a copy of the lift of the loop downstairs. This would push this winding number to the next piece with the same winding number. So the piece that we start with now has winding number W, and all those winding numbers are now transferred to the next piece. And then we can keep doing this, pushing this 2W to the next W, arriving at this situation. And we can repeat this process until we localize all the winding numbers into a single piece along this boundary and realize all the others as genuine disks, because they now have winding number 0. So by taking a suitable cover where every loop downstairs like this gets unwrapped by a huge covering degree, then we realize most disk-like pieces as genuine disks in the finite cover. And this is the key idea in the asymptotic promotion and proves the key lemma.